Fine. So today we'll be starting with the new topic, that is concurrency. Okay. And concurrency, what does it mean? What kind of problems can arise because of concurrency, and how these problems can be tackled? That is the topic that we are going to discuss. And what kind of problems can arise? So mainly there are three types of problems: mutual exclusion problem, starvation, and deadlock. And we'll be talking about different available solutions, different designs which are there already to handle these problems. So let us start with what is concurrency. There is a typo in this slide which is going to be repeated again and again. It is principles, not principals, right? So there is some typo. So please bear with that, as this is PDF and I cannot change it. So you need to bear with that. So first we'll understand what are the principles of concurrency, and then we'll be discussing different possible techniques, software approaches, hardware supports, and this other things that you see here. This three things: semaphores, monitors, and message passing. These are the three techniques, which is, or you can say, these are the three methods supported by either OS or programming language to achieve mutual exclusion. So that is what we'll be discussing after that. And finally, we will discuss one classical problem, that is readers writers problem. Okay. And today I'll try to complete the first part, principles of concurrency, and the third one, what kind of hardware support can be there to achieve mutual exclusion. So mainly our focus is on mutual exclusion and then after synchronization. So let us talk about multiple processes, because now concurrency. Okay, can anyone tell me what do you understand by concurrency? You can unmute and you can answer, no problem. What do you understand by concurrency? Is it same as parallelism, or it is different from that? Anyone? Definitely it is different from parallelism, right? Because we have discussed that when we have only one CPU or one processor, and still we want to achieve the effect that multiple programs can run on single CPU at the same time, then concurrency is the idea which helps. And there we use interleaving. So that we'll be discussing again, what is interleaving and overlapping. Even in multiprocessor, when you have multiple cores in your CPU, and if you are using that, still you can have this idea of concurrency, right? And that is why whatever we are going to discuss, mostly of course we will be discussing it in the context of single processor, but most of the idea, most of the design, they are applicable to multiple processor systems also in one or other way. So let us discuss what is this. Central to the design of modern operating system is managing multiple processes. That is the central idea for any operating systems. Central job for any operating system is to manage multiple processes, be it multi-programming system, be it multi-processing system, be it distributed processing system. In any kind of such system, when you have OS, the first job of this OS is to handle multiple processes. And big issue is the concurrency. And when you have multiple processes, there is a concurrency, and concurrency is a big issue to handle, because OS needs to manage the interaction of all these processes. And when I say interaction, okay, so what do you understand by interaction of multiple processes, be it on single processor or multiple processor? What is your understanding regarding interaction of processes? Yes. What do you think? When I say two processes are interacting, does that mean they are talking to each other? Does that mean so? There can be different ways of interaction between two processes, through sharing, through message passing, through communication, right? They may require some kind of synchronization, they require some kind of cooperation, right? So all these are different modes of interaction. We'll be discussing this modes of interaction also. And that is a big issue. When you have multiple processes running concurrently, the interaction between these processes need to be managed. And few examples where this concurrency arises. For an example, in a single processor system, if you have multiple applications and each application may be being executed by a single process. So now you have multiple processes which are executing multiple applications, and they may need to communicate. They may need to share, of course, they need to share time because they are running on a single processor. So there is some kind of interaction between these processes, direct or indirect, and OS has to handle that. So we have already discussed different scheduling algorithms, right? So that is one job of OS, to handle this concurrency, to schedule one process at a time according to some criteria. You may have some structured applications where you have, in one application, you may have multiple jobs which are being executed through different processes. If you remember, I told you that nowadays you know, this latest browsers that we are using, when we run that browser, it is possible that they are running, they are actually executing multiple processes, not on a single process, right? So you may have such kind of structured application where you have multiple jobs being executed, through multiple processes. Then even sometimes the design of operating system is such a way that they are implemented as a set of processes or threads. We have also learned that in thread also we learned that you may have kernel level threads where there is a thread, then microkernels where different modules are running as different processes. So all these are possible examples where you have concurrency problem, and that need to be handled. Either this concurrency is there at application level, or it can be there at OS level itself. Now, before we start understanding concurrency and the problems which can arise because of that, and how can we solve that, first we need to understand certain terms. Atomic operation, you might have gone through this subject called database. Is it so? Have you gone through that subject, database?
Yes, sir.
Yeah, there you might have learned about atomicity. One property for this database, atomicity. That means whatever job it is doing, it should be done atomically. That means when it is being done, no one can interrupt that, and it should not be interrupted, and it can be done in a single go. So atomic operation, a sequence of one or more statements that appear to be indivisible. That is, no other process can see an intermediate state or interrupt that operation. So you must be very well aware of this term, atomic operation. Then another term is critical section. Of course, we'll be discussing more on these terms as and when they come, but this is just an idea that I'm trying to give you. What is critical section? A section of code within a process that requires access to shared resource and that must not be executed while another process in a corresponding section of a code. So to simplify this idea, let me give you one example. Let's say there are two processes who need to access same file or same data, same variable maybe. So they are sharing something. There's two different processes, they are sharing something. And if one process is executing certain statements which is going to affect the state of that shared resource, at that time no other process should be allowed to access same section which is affecting the particular resource state. Okay, and that kind of section of the code which can be executed by only one process at a time, then that is called critical section. If you are not getting, don't worry, we will be having this term again and again, and you will get better idea later on. Then there is a term called deadlock. it's a situation in which two or more processes are unable to proceed because each process is waiting for another to do something. Okay, and you might have seen this real world example of deadlock, maybe at traffic, you know, maybe at crossroads, where you might have seen traffic jam, and that is the simplest and best example to explain this term called deadlock, because everyone wants to go further but they cannot, as one is blocking the way of other. Then there is a similar situation to this deadlock that is called live lock, a situation in which two or more processes continuously change their states in response to change in the other process without doing any useful work. Actually they can proceed, they can execute, but they are not doing any useful work because they are changing their states depending on the results from other process. And because of that, though processes are able to do something, they are active, they are able to do something, but they are not doing, they are just you know, passing the time, and that is called live lock. Then the term called mutual exclusion, the requirement that when one process is in a critical section that accesses shared resources, no other process may be in a critical section that accesses any of this shared resource. So when some process is in critical section which is actually doing some work on some shared resource, no other process is allowed to enter in the same critical section, same code. No other process is allowed to execute same code. Okay, and that requirement is called mutual exclusion, and that needs to be achieved if you want coherent state of your resource. Then there is a race condition, a situation in which multiple threads or processes read and write a shared data item, and the final result depends on the relative timing of their execution. Let's say there are two processes who are changing this variable value a. There are two processes, both are changing the value of a. Okay, but which value will be the final value? It depends in which order this process are executed. If there are two processes 1 and 2 and both are changing value of variable a, if process a executes first, let's say process 1 changes the value of a, that is to 2, and process 2 is changing the value of a, that is to 5. If process 1 executes first and changes the value of a, and then process 2 executes the code and changes the value of a, tell me what will be the final value of a? Yes, are you getting this? What value will be there after both processes had changed the value of variable a? Okay, so I think you people are still in festival mode. Maybe you are sleeping. The value which is changed last, right? That is 5. Let's say it is 5. So the race condition is a situation in which multiple threads or processes read and write a shared data item, and the final result depends on the relative timing of their execution. Relative timing of their execution means which process runs first or changes that value first, and which process changes that value last. So here is the race condition. This is called race condition situation. But who is the winner of this race condition? Normally in real life, who is the winner of race? Who comes first, right? Who comes first, he or she is the winner, right? But here, the process which executes last and changes that particular shared resource, that particular state will be there at the end. And that is why that process, you can say, is a winner of that race condition. But this race condition should not happen, and we'll see how we can solve that with the help of mutual exclusion. Uh, starvation. Again, when I say race condition, okay, you need to understand one thing. When I say race condition, it does not mean that two processes cannot change the same variable. Okay, but they need to change that variable in an appropriate manner. For example, whenever you are doing any database operation, it does not mean that two different client requests cannot change some particular data. Okay, but then it must be done in coherent way. It should not leave that data in some corrupt mode. Okay, so that we will see, and that is what we are talking about race condition is about, right? We are not saying that two processes cannot change same variable. They can, but in a particular manner. Then there is a term called starvation, a situation in which a runnable process is overlooked indefinitely by the scheduler, although it is able to proceed, and it is never chosen. This normally happens when you have scheduler which is working based on priority, which schedules the processes based on priority. And if there is a endless flow of higher priority processes, and because of that some lower priority process never gets a chance, even though it is ready to run, but it never gets chance to run, to execute, then that process is called starved process. Okay, so these are a few terms that you need to have some idea about. And one more idea, that is interleaving and overlapping processes. This is the two different ways for concurrency. When you have a single processor, the processor time is being shared among multiple processes, so they are executing in an interleaving manner. When process 1 is executing, at that time process 2 and 3, they may be in ready state or block state, whatever is the possibility. Then once process 1 completes is part of the job, or maybe it is getting blocked and waiting for some other resource, at that time now another process. Basically this is interleaving because there is a single processor, so at a time only one process is running, you can see that. Okay, though here it is very conveniently shown that this is a block state, maybe it is a runnable state, we don't know, maybe this is using round robin, so there can be any other state, but running state at a time only one process is running, and you can see that this is called interleaving. And when you have multiple processes, there is a possibility of overlapping at the same time on different processor, different processes can execute. So you can see here there are three processes. Okay, can you give some conclusion that, okay, let me tell you one thing, this three processes are executing only on two processors, not, there are not three processors. Okay, they are executing only on two processors. So can you tell me which two processes are executing on one processor and which one process is executing on another processor? From this diagram, can you
2 and 3 on
yeah,
2 and 3 on one processor and
exactly.
process 1 on.
Yeah, 2 and 3 are on single processor because they are interleaving, right? Whereas process 1 can execute in parallel of any of these two, and that you can see here, right? So this happens, you can see that there is interleaving between 2 and 3, and there is overlapping between 1 2 and 1 3, and that is possible because there are multiple processors. So these are the two different ways. When you have a single processor, it is concurrency you can have only through interleaving of processes. And when you have multiple cores or multiple processors, at that time processes can execute in interleaving fashion as well as in overlapping fashion. Now, what are the problems with this concurrency? We say that concurrency is a problem that OS needs to handle. But what kind of problem? First of all, they are sharing a global resource. Okay. Concurrency, normally when concurrency is there, multiple processes may be sharing some global resource, be it hardware resource like printer and all those stuff, disk and anything, or it can be some variable or some file data, some database system, which is soft resource, you can say. But ultimately, they can be sharing some global resource. And when two processes are sharing resource, if they cannot handle that sharing properly, there are very high chances that the resource may be left in some undesired situation, may be left with some corrupt mode. Okay. Um, have you ever observed this kind of problem anywhere before? Maybe in real world, have you seen this kind of problem where two people are trying to use same resource and they are ultimately damaging that resource if they are not handling it properly. Yes. TV remote. Can we say that two are trying to use this at the same time? Maybe they are finally damaging that remote. So when you have a shared resource among multiple processes, it needs to be handled carefully. So that is one problem. Optimally managing the allocation of resources, that is another problem, because multiple processes, they need different resources, they need some shared resources. So how to allocate resource, and at what time which resource should be allocated to which process, so that resource allocation job is also going to be difficult. And the third one, difficult to locate programming errors, as results are not deterministic and reproducible. Sometimes what happens, that it is difficult to identify that whatever programs you have written, you never know that this particular code may create some error at runtime. Okay, because that particular situation may not, it is not going to happen every time when you run that code. Only sometimes it is going to it is going to demonstrate that behavior, which may not be catch during testing. So that programming errors are becoming difficult to locate, as results are not deterministic, and that is the another problem with this concurrency. So this third type we will be discussing when we will be discussing software approaches. So these are the three main problems that needs to be dealt with by OS to when we have this concurrency, when we have multiple processes. So you can see one simple example here, right? This is one process, you can say a block of code. What it does, very simple, takes one character from keyboard maybe and store it in some another variable chin. Then this chin provides its value to chout, it stores there, and this put character function put that value on the screen. So very simple program, echo program, which takes one input from the keyboard and put it on the screen. But meanwhile, in between, it is copying that keystroke in some another variable also. So definitely this is one more instruction which is being executed. Now assume that the above code is being executed by multiple processes through shared memory, okay, where chin variable is a global variable. Just assume that way. Shared memory means there is some variable which is being shared. Let's say chin is a shared variable, global variable, which can be shared by multiple processes. So every process which has this chin, it is pointing to the same memory address. So now what are the possible problems here? Just think about this scenario. Process P1 invokes the echo procedure and is interrupted immediately after getChar returns its value and stores it in chin. So at this point, the most recently entered character X is stored in variable chin. Very simple. P1 process executes this code, and after executing this statement, where it has stored, let's say, X value, X key in chin, once this statement gets executed, this process P1 gets interrupted and it is going to be block or something like that. Okay. Maybe it is round robin, it has completed its time, and maybe now it is going to join the ready queue, whatever the situation, but that process is now interrupted and it is no more running, and new process is scheduled. Let's say P2 gets scheduled. So process P2 is activated and invokes the same echo function, which runs to conclusion, inputting and then displaying a single character Y on the screen. So now P2, what it does, it also executes the same code. It gets some character Y, store it in chin is given to the chout, and finally it is printing that chout. Finally, it is printing the chout. Okay. And P2 completes this job before it gets interrupted. So can you tell me what will be getting printed by P2? P2 is printing Y character. Whatever it is getting, that is the same character which is printed. Now, let's say P1 gets next chance. It is resumed. It is resumed. So tell me what P1 will be printing now, because it has already executed this part. So it will continue from this. Now it will start again from this point. Pointer program counter is at this point. So it will continue or resume from this point, and then it is going to print. So what it will be printing? What it stored here in CH in P1 process? It stored X, but it is printing Y because CH in variable, which is global variable shared by multiple processes, and the second process has changed this value of CH in. It has replaced that value by Y. So CH in is currently containing Y, and that is what is executed even in P1, and P1 is also going to print Y. And this is one race condition. This is nothing but race condition. Two different processes are sharing the same variable. And this is happening, this same variable, when it is shared by two processes and it is not properly handled, then this kind of problem occurs. This is the problem you can see on a single processor system. But what if you have multiple processors? So very similar example, process P1, okay, let's say at this point it executes this, and then maybe it is doing something else, or maybe, yeah, it is doing something else. Okay, and when process P1 is doing something else, at that time process P2 on another processor, it is trying to get CH in. Okay, now both are doing here CH out equal to CH in, and then here it is putting character CH out on the screen. At this point P2 is putting on the CH out. Now in this example, again, okay, so let us understand what is. So if we enforce a rule that only one process may enter the function at, okay, now see, this is the solution actually. So if we complete this, here also the CH in is a shared variable between P1 and P2, though they are executing on a different processor, because CH in is nothing but the memory. It is in some variable stored in some memory, and memory is common between multiple processors. Like if you have currently whatever systems you people are using, I am using, they all are multi-processors, but ultimately memory is same. So just assume that this CH in is still a shared memory. So P1, whether it is executing on one processor and P2 is executing on another processor, still the problem is there, because CH in, the resource is still shared among P1 and P2. So whether it is a single processor or multiple processor, this code, if it is executed by multiple processes where CH in is a shared resource, CH out is not a shared resource, okay? CH out is a local resource, local variable, whereas CH in is a global variable. So in that case, whether it is a single processor or multiple processor, in any case, the problem is still possible. And one thing that you need to understand, when you do this, when you execute P1 and P2, it is not necessary that always this situation occurs, because it depends on the relative speed of P1 and P2 on a single processor or multiple processor. If P1 completes first and then P2 executes, then there is no problem. Then there is no problem. Or alternatively, if P2 completes first and then P1 executes, still there is no problem. But when they are executing, you know, at the same time or interleaving, and then there is a problem. Are you getting some idea about this? Yes. Guys, are you getting some idea? Are you understanding what I'm trying to explain? Okay. Please stop me and ask if you have any query. Now, so what can be the solution to this problem? What is the first solution that comes to your mind to solve this problem? What is the first thing that comes to your mind? Anyone? How can we stop this problem? this race condition. Okay, start P2 after completion of P1 or other way, right? Any one process should be executed at a time completed, then only another process should be executed. If that is there, can we achieve this performance? Because now what you are doing, you are converting your time sharing system into serial processing, one process at a time, because you don't know which processes are sharing which resources. Maybe that is not possible. So at a time you are allowing only one process to execute. And even if you have multiple processors, let's say in this case multiple processor, how will you solve this problem? So the idea that you have given, someone has given, that one process should be executed after another process, that can be limited up to some portion of that code, only to some portion of that code which is sharing some resource like chin. So this portion of code at a time should be executed only by one process, and that is called mutual exclusion. And that section of the code which should be executed only by one process at a time, until unless that process completes that code, that section of the code, no other process should execute the same section of code. That idea is called mutual exclusion, and that section of code is called critical section, where resource is being shared. That critical section, that section of the code is called critical section. So enforce single access, that is a solution. So if you enforce a rule that only one process may enter the function, that echo function, because this echo function is the function which is having some shared resource, which is changing this shared resource, right? So if we enforce this rule that at a time only one process can enter the function, this echo function at a time, then P1 and P2 run on a separate or same processor, doesn't matter. Okay, P1 enters echo first, P2 tries to enter but is blocked. These are the possible situation. Let's say P1 enters echo first in this case. Here, let's say even in this case, P1 enters echo function first. So when this P2 is trying to enter in this echo function at this point, it will be denied. P2 tries to enter but it is blocked, and P2 suspends. And then P1 completes execution, and then after P2 resumes and executes echo. So basically, whether it is a single processor, multi-processor, doesn't matter. But if one process is executing in some critical section, same critical section cannot be entered by other process until unless that process which is already there in critical section completes. Till then, no other process can enter in the same critical section. Again, this is one critical section. There can be multiple critical sections which are using different resources. Someone is trying to say something. Yes, Harsh? Do you have any question? Okay. So let us reiterate this race condition. Let us understand it again. The race condition occurs when multiple processes or threads read and write data items, and they do so in a way where the final result depends on the order of execution of the processes. The same idea that we just discussed, right? This echo function, let's say there are two processes, P1, P2, P1 executes and get character X and print out, P2 gets character Y and print that. But ultimately what you see on the screen, as per this example, you see two Ys, because the resource is being shared such a way that it is disturbing the state of the variable. The final result depends on the order of execution of instructions in the multiple processes. So we have seen that how and which order this instructions are executed in two processes. Based on that final result, you see that both are printing Y. Now, what are the operating system concerns regarding this? So what design and management issues are raised by the existence of concurrency? We have already talked about that. What are the difficulties in handling concurrency, right? Those are three things. Do you remember those 3 points? Difficulties in concurrency. These are the 3 points. One problem is there is a globally shared resource. Then OS needs to manage this allocation of resources optimally, and it is difficult to locate programming errors. So now further the discussion on that, to when OS needs to manage this concurrency, what it needs to do. So first, OS must keep track of various processes. How OS keeps track of various processes? Okay, that this process is doing this and this is the next instruction that should be executed, and somewhat like that. How OS does all these things, and that we have already discussed in chapter 3 through that process control block. OS keeps track of various processes with the help of PCB, and that is what we have discussed in chapter number 3. Then OS must allocate and deallocate resources. Okay. Protect the data and resources against interference by other processes. If one process is working with one file, and if another process wants to work with the same file, OS needs to manage that security. I mean, it needs to manage that resource, that particular file, in a way that no other process can interfere in the another process, right? So that is required protecting. Ensure that the processes and outputs are independent of the relative speed of the processes, and that is the main job. Now, what we just discussed as an example, this echo, when you have two processes executing same code, which is sharing some resource, in that case, OS needs to make sure that these processes are executing this code such a way that it does not leave this particular data item in some corrupted mode, right? So that is there. Ensure that the processes and outputs are independent of the relative speed of the processes. OS needs to make sure that in whichever order these processes are getting executed, the data should not be corrupted. Now, I told you that process interactions can be in a different ways, right? And they need to be managed. That is the main job of OS. When you have multiple processes, the main thing is to handle the interaction between these processes. Now, there are different ways for these processes to interact. Okay, and here in this book, they are given, author has written this idea in the terms of degree of awareness. Okay. Now, what kind of interaction can be there based on this degree of awareness? First possible way is where processes are unaware of each other. You don't know that other processes are also there, which are going to use the same resource that I am going to use. For example, there are multiple applications who are trying to print on a printer, and printer is a single resource. But your application doesn't know that other process is there, which is also trying to print. You don't know that. And same way, other process does not know about it. So this is one kind of competition amongst processes. Because they don't know about any other process, they think that I am the only one who is using the resource. But actually, what is the situation? That multiple processes are trying to use the same resource, and there is a competition that who will get that resource at particular time. And what kind of influences can be there of one process on the other when you have this kind of interaction between processes, where processes are competing to each other for some resource without knowing about others. Results of one process independent of the action of others, because one process has nothing to do with other process. Okay, but the timing of processes may be affected. Now, what is that? Let's say P1 and P2 both try to use the same printer, but if P1 gets the chance to acquire that printer, now P2 will be delayed because P2 has to wait for that printer, or vice versa. So when you have competition and resources allocated to one process, other process has to wait, and that's why timing gets affected. But then what kind of potential control problems can be there? So these are the three problems which can be there when you have this kind of process interaction. Without knowing that other process is there, if multiple processes, they are competing for the same resource, there can be a problem of mutual exclusion. Mutual exclusion is a control problem, right? That you need to achieve actually mutual exclusion. You need to achieve mutual exclusion, but if it is not there, then that resource that is being shared, that is being used, may be left in some undesirable state. There is a possibility of deadlock. Okay, there is a possibility of, okay, what is that problem here? Deadlock, how this problem can be there. So let us say there are two processes and both are sharing, let's say both are required two resources. Okay, now process one has acquired first resource and then it gets interrupted or whatever, and process two executes and it acquires second resource, let's say. But both process cannot complete further until unless they get the other resource. But P1 has acquired first resource, which it is not leaving. P2 has acquired second resource, which it is not leaving. Now P1 cannot complete without P2 resource, without their second resource. P2 cannot complete without first resource, and both cannot complete because other resource that they require, it is there with other process, and this is deadlock situation. And that is potential control problem when we have multiple processes which are competing for the resources. There can be starvation also. Okay, there can be starvation also. Like what is starvation? If there is a single resource which is required by multiple processes, and let's say there are some higher priority process continuously coming and use that resource, lower priority process will never get that resource, so it is starved for that resource. So these are the possible control problems which can be there when you have this kind of relationship, competition relationship between multiple processes. Then there is another degree of awareness, like process indirectly aware of each other. There is a process, let's say whenever you create any application to access database, you must be aware that your application, apart from your application, there can be other applications which are accessing the same database. That is possible. You know about that, but you don't know which process. You don't know about that process, but you are aware that there can be another process which is executing, which is using same database. And there you need to make sure that whenever you use that particular resource or database or whatever, you use that resource in a good manner without affecting its state when it is being used by other process. So that is called cooperation by sharing relationship. Now that multiple processes who may not be directly knowing each other, but they know that there can be other process which is using the same resource. So they cooperate and they share resource in a better way. Sometimes results of one process may depend on information obtained from others. Okay, let's say there is one process which is inserting data and there is another process which is consuming that data. So the process which consumes the data from database, it is waiting for other process to provide some data first. So that is one possibility, that there can be some sharing. And timing, definitely timing of processes may be affected. If one process is already using that data, other process is not allowed, maybe it is delayed. So that is another way. Now problem, the same problem like mutual exclusion, deadlock and starvation are possible. These are the same problems that are there with this type of interaction. One more problem which is entered is data coherence, which is also possible. Data coherence. Basically, if these two processes, they are not cooperating properly and they are trying to execute same variable or same data and try to write some other data on that same variable at the same time without taking note of other process, the data which is now finally emerged, it is not in coherent mode. This is very much related to your database atomicity, right? Whenever one process is writing some data in the database at particular row, no other process should be allowed to write or change that same row. Otherwise, there will be some corrupted data. So that problem can be there when you have interaction between processes in the form of cooperation by sharing. So this is another possibility of interaction. Another type of relation between processes where there is a cooperation by communication, where process directly knows that this is the other process that I am working with. Okay, they know each other directly. Okay, and again, the influence is very same, but there is no problem of mutual exclusion, only deadlock and starvation, not data coherence. There is no such problem of mutual exclusion. Why? Because normally when processes are directly aware of each other, okay, their communication, there is some communication between them, maybe through message passing. That is the best way for communication. One process passes some another message, okay, some message to other process. That process again, so basically it is like client server kind of system can be there. And these are the two multiple there are two processes which are maybe interacting with each other, but there is no problem of mutual exclusion because they are not actually sharing resource without knowing about others. So what kind of problems can be there? Maybe there can be a deadlock. And the very simple example to understand here why deadlock can be there, and that is for consumable resources. Message is a consumable resource. Now, what is renewable resource and what is consumable resource? Let us understand that. Renewable resource is a resource when it is used by one process can be used by another process afterwards, like printer. If one process has used printer to print something, now other process can use the same printer to print something. That is renewable resource. Consumable resource is like a message. When one process sends some message to other process, once other process reads that message, now it is consumed. Now the same message cannot be used by other process, right? That is consumable resource. Message is a consumable resource. Fine. So when one process is aware of another process directly, it knows about that process and they are sharing something. I mean, they are communicating with each other through, let's say, messages. Fine. So there is no much sharing between them directly. But what is the communication between them? That process one sends one message to process two. Okay. And process two also sends some message to process one. Now, but the problem is, let's say both processes, before they proceed further, they want to get some message from other process. So process one is waiting for the message from process two, and process two is also waiting for some message from process one. Then only they can continue. So this is a deadlock. This is a deadlock because P1 is waiting for some signal from P2 that, okay, you tell me that I go, so I will go. P2 say, no, first you tell me that you go, then I will go. So both are waiting for other signal. And then there is a deadlock. Okay, so that is possible when you have communication like this, through message passing. But there is no mutual exclusion problem because there is no shared resource. There is no directly shared resource. Then there can be a starvation. For example, there are three processes, P1, P2, P3. P1 and P2 communicate with each other. P1 and P3 also communicate with each other. But P3 is a lower priority process than P2. So P1 always communicate with P1 continuously, and it is not communicating with P3. So what is happening to P3? It is starving for some communication from P1 so that it can go further and it can proceed. So deadlock and starvation are possible control problems in this kind of system where you have communication between two processes which know each other. And we will see one good example of this, that is producer consumer problem. But in that, there is not only this, it is producer consumer is a standard problem which shows communication as well as cooperation by sharing. We will see that. So there is all these three types of problems are there. But these are some idea that how processes can interact in with different relationships: competition, cooperation by sharing, and cooperation by communication. So competition among processes for resources. So that we already discussed, right? We have already discussed this. So need for mutual exclusion is there, and it is a potential problem. Now, so let us focus on this part now. Competition among processes for resources, and in that, again, let us focus only on this problem, mutual exclusion. Deadlock, we will be discussing deadlock problem and how to handle that problem in OS. That we will be discussing in next chapter. Okay, that we will be discussing in next chapter. So this is chapter number 5 from your book, where we will be discussing mainly on mutual exclusion and synchronization. So let us understand the requirements of mutual exclusion. So after discussing all this, you can say introductory part to understand these problems and how we can solve it, that is what we discuss. But now we will be starting the discussion, actual discussion of the mutual exclusion. Are you with me at this point? Are you getting what I'm trying to explain? Yes, guys, please let me know whether you understand this or not. Right? Okay. So let us continue. Let us understand requirements of mutual exclusion. Only one process at a time is allowed in the critical section for a resource. Now, when I say critical section, you need to understand that critical section is a code of section of the, you can say it's a particular code section which is sharing same resource. So when you have critical section, it is not critical section for all the processes. It is critical section for those processes which are using that particular resource which is being altered or which is being used in that particular code section. So that is critical section. So if it is working on different resource, then it is not critical section for all processes. I hope you understand that idea. Okay, so you may have multiple critical sections based on the resource which is being used inside that code section. Now, resource can be variables, resource can be files, resource can be like printers and other devices. Anything can be considered as resource. A process that halts in its non-critical section must do so without interfering with other processes. Now, there is a big code which is being executed by some process. Out of that big code, only small part can be a critical section and other part can be a non-critical section where it is not using any shared data. So when any process is blocked or it is halting in other part of the code which is not critical, then it does so such a way that that thing is not going to interfere in other process. Other process now then after should be allowed to enter in critical section without any problem. So we will see again this thing with the software approaches. We'll try to understand what it says. It must not be possible for a process requiring access to a critical section to be delayed indefinitely, and no deadlock or starvation should be there. So this is another requirement of mutual exclusion. If you implement mutual exclusion, see, mutual exclusion is not a problem. Mutual exclusion is not a problem. Okay, mutual exclusion is a situation, is a condition that need to be achieved by the OS in certain case. Okay, so when you try to achieve mutual exclusion, make sure that you achieve mutual exclusion in such a way that if one process, let's say one process is executing in critical section, at that time no other process should be allowed to execute in the same critical section, right? But if one process which is already executing in critical section, if it holds there, if it is blocked while in the critical section and it is blocked there for a long time, or maybe it is never coming back, what will happen to other process? Can that process be allowed to enter in critical section? What do you think? If one process which is already executing in critical section, let's say it is crashed, maybe it is crashed, that process is crashed, but it was in critical section. As it was in critical section, what OS thinks? There is some process which is in the critical section. Will it allow to other process to enter in the critical section? Yes, I'm asking you people. Definitely not. And that is why what will be the problem? The other processes will be indefinitely delayed to enter into the critical. They will never get a chance to enter into the critical section. And there should not be any deadlock or starvation situation when you try to achieve this mutual exclusion. So when you achieve mutual exclusion, only one process at a time, a process that halts in non-critical section must do so without interfering other processes, and it must not be possible for a process requiring access to a critical section to be delayed indefinitely, and there should not be deadlock or starvation. So these are the requirements. Some more are there. A process must not be delayed access to a critical section when there is no other process using it. That is also there. If one process, if no one is using critical section, if any one process is asking for the critical section, it should be immediately granted that access. So there should not be any such problem. No assumptions are made about relative process speeds or number of processes. So when you try to implement this mutual exclusion, you cannot assume that, okay, this process will execute first and then after this process will execute. No, you cannot have such assumption that in which speed which process will be executing, which will be executing first, which. So you cannot rely on that while achieving mutual exclusion. While implementing mutual exclusion, you cannot assume about relative speed of the processes. And a process remains inside the critical section for a finite time only. That is another important condition. When you try to implement mutual exclusion, make sure that a process which is executing in critical section, it will remain in critical section for finite amount of time. Otherwise, it is possible that other processes will be delayed indefinitely. So these are the main requirements whenever you want to achieve mutual exclusion. Whenever you need to implement mutual exclusion, in whichever way, you need to keep these things in your mind, how you can do that. These requirements must be satisfied. Then only that is the proper mutual exclusion solution. Now there are different approaches to mutual exclusion. First is software approach. Software approach means the processes, whether it is system process or application process, would be required to coordinate with one and another to enforce mutual exclusion without any support from programming language or the OS. Okay, this software approach, different software approaches, they are given in not the actual chapter, they are given as the appendix, but we are going to discuss them because they are very important to understand the idea itself. Okay, and here in software approach, basically the way you write your programs and when they execute as a process, the way you write your program, you need to write such a way that they are coordinating with each other. Okay, so we'll try to discuss this software approach. There is hardware support also. There is another approach where you get some hardware support to achieve mutual exclusion. So this approach involves disabling interrupts or the use of special purpose machine instructions. Of course, this software approach, they are very prone to high processing overhead and bugs, because ultimately when you write your application, let's say you are writing some program, it is your responsibility that you achieve this mutual exclusion and you do not interfere in critical section. That is your responsibility as a programmer, but then it is very high prone to processing overhead and bugs. So that is the problem with this hardware support. It reducing overhead, but still unattractive as a general purpose solution. It is a better than this software approach, but still it is not general purpose solution. What is general purpose solution to achieve this mutual exclusion? That you should get some support from programming language or OS. If you know Java, I don't know how many of you know Java. There is a term called synchronized. Have you heard about that term, synchronized? So that is one construct which is provided by Java language to achieve mutual exclusion and synchronization. Okay, so if there is some support from programming language or OS itself, then it is the best solution to achieve mutual exclusion, rather than writing yourself or only getting support from, only relying on the some support from hardware. Okay, even when this programming language or OS provides some support, definitely they take some support from hardware also. Hardware must have some support, but not directly. You get that support through programming language or OS. So these are the three different approaches that we are going to discuss how to achieve mutual exclusion. And first we'll start with hardware support, which is very simple. Though I have shown here that we will discuss first software approach, but then I thought, let me discuss this first and then we'll be discussing software approach, because hardware supports are very simple to discuss. So let us continue with that first. Hardware support. Okay, a very simple thing that you need to understand, why there is a problem of mutual exclusion, or where you require mutual exclusion. When there is a critical section, then you require mutual exclusion. And when the critical section problem is there, if one process is executing in critical section, at that time, if other process executes in the same critical section, then there is a problem. But that happens, especially in single processor system, that happens only if the process which is already executing in critical section gets interrupted or it is getting blocked. Then only other process get a chance to run. And if other process gets a chance to run, then only it can enter into the same critical section. So if we remove this problem from its very root, that if one process which is executing in critical section should not be interrupted or cannot be interrupted, your problem is solved. Your problem is solved, because there is a single processor, one process is executing, it cannot be interrupted, so no other process can execute. If no other process can execute, there is no problem of race condition. There is no problem of multiple processes executing the same critical section. There is no such problem, and mutual exclusion is achieved. So this is very simple solution by disabling the interrupt. Okay, so whenever there is a critical section, let's say this part is critical section. So before entering into the critical section, what is done? You just disable the interrupts with the help of some hardware support. Disable that interrupt, and once you complete critical section, then enable the interrupts so that you can be rescheduled. So that is that is the possibility. That is one possible solution. Are you getting this? Are you getting that how this helps? Okay, very simple solution. But what do you think? Is it going to work? Is this solution going to work when you have multiple processes? Will this solution work when you have multiple processors? No, definitely not. Because in multiple processors, if you cannot interrupt one process which is running on one processor, but there is another processor where other process can run and enter into the critical section. So can we solve this problem for multiprocessor? So what are the issues with disabling interrupts? Again, there are not only one issue, there are multiple issues. When you use this solution through hardware, you just disable the interrupts, then there are few problems. What are the problems? The processor is limited in its ability to interleave processes. Normally, critical section code, if it is a very big code and you disable the interrupt, it means only one process can run at that time and no other processes can interleave. So definitely it is going to affect the ability of interleaving of that processor. So basically performance will be reduced. The response to the external events get delayed, because interrupt is not only about executing another, it is not about interrupt to remove that process and allow another process to execute. The interrupts can be for different reasons also. Time interrupts can be there, device interrupts can be there, there can be some signals, so there can be different interrupts. And response to some, let's say some interrupts are very priority interrupts that they should be handled properly, they first handled. So the response to these external events get delayed. Okay, if you disable the interrupts, process will never get that interrupt and it will never able to handle it. OS will never handle it. So the process response to that external events will be delayed. And this approach will not work in a multiprocessor architecture. So these are the three problems you can face if you use this solution to achieve mutual exclusion. Okay. So what can be the other way around? So you can use some special machine instructions. Okay, rather than disabling interrupts, you can use some special machine instructions. Okay, how it works, let us understand. At the hardware level, access to a memory location excludes any other access to that same location, and that is for sure. When there is some memory location, main memory location, which is being accessed by one process, at hardware level, it is not allowing any other process to execute the same to access the same memory location. Do you agree with that? At a time, that memory address, one particular memory address at hardware level can be accessed only by one process. No multiple process can access the same memory address. So can we use this feature? Can we use this characteristic to achieve mutual exclusion? Let us see. With this as a foundation, processor designers have proposed several machine instructions that carry out two actions atomically. Now this is atomic instructions, right? So there are two actions, two things are done atomically without any interruption, such as reading and writing or reading and testing of a single memory location with one instruction fetch cycle. Now, if two things can be done in one fetch cycle without any interruption, like reading and writing or reading and testing, then we can devise one special machine instruction which help us to implement mutual exclusion. So let us see how it can be done. During execution of the instruction, access to the memory location is blocked for any other instruction referencing that location. So now there is a special type of instruction which will be doing two things atomically without interruption, and that is reading or writing or reading and testing. And if that can be achieved without any interruption, you can make sure that you achieve mutual exclusion. Let us see how. So there are two such instructions, and again there are multiple such instructions possible, but we are going to discuss these two which are given in your book. And these are the hardware instructions. Okay, these are some hardware instructions: compare and swap instruction, or you can use exchange instruction. Compare and swap is also called compare and exchange instruction. Now what is this? So let us understand the general idea. Okay, first of all, basically what we are trying to achieve here, whenever any process wants to execute or wants to enter in the critical section, before that it needs to check something. It needs to check some memory area. If that memory area contains some specific value, then only that process can enter into the critical section. It is like a token. Whoever wants to enter into the critical section first needs to get a token, but there is only one token which can be there with only one process at a time, and that token is nothing but that memory area. So if you lock that memory area, if you say that, okay, I have placed my, okay, if you know that, I mean, you might be aware of that tradition or that customs that people follow at bus stands. Whenever they want to book a seat without any proper reservation system, what they do? If there is a very heavy crowd, okay, and they are unlikely to get seat once they enter into the bus, normally what they do? Are you aware of that idea? I mean, are you aware of that custom? I should not call it custom actually. It's a practice that people follow. From the window itself, they drop their hanky or some, you know, some kind of stuff on particular seat and says that I have reserved that, right? Put their bags on the seat or likewise from the window itself. So that is one kind of token, right? So this instructions, hardware instructions, through that, what process achieves? It gets some token. And once it gets that token, it means now that process can enter into the critical section. Fine. So again, we are going to stop here today. And this compare and swap and exchange instruction, how they work and how they help to achieve this mutual exclusion, that we will discuss in the next lecture on Wednesday. Another thing, at least for 2 to 3 Fridays, I am going to take extra lecture at the same time, 8 to 9:30. How many of you, I mean, are you comfortable with that? Only thing that I'm asking is, do you have any other schedule on that time? There is no other question, right? If you have any other schedule on that same time on the same day, then we can shift it. Otherwise, I'm going to take those lectures. Friday, 8 to 9:30 morning. Do you have any other schedule? Priyesh bhai, will you please coordinate this?
Yes, sir.
Will you please look at this, that they have any schedule on Friday 8 to 9:30?
I will make it confirm from them and I will
So please confirm that, and at least 2 to 3 Fridays I am going to take extra lectures on Friday
tomorrow
8 to 9:30.
itself I will make it clear, sir.
Okay, so please let me know whether it is suitable for them or not.
Yes, sir.
Or otherwise, just ask them and tell them to give me some suitable slot.
I will do that, sir.
Okay.